Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Soumya Roy with us today. Hello, Soumya.
Hi, Frank. Thanks for having me on this.
Well, thanks for agreeing to talk about your very lovely article, which we'll get to here in a little bit. And Soumya, what's your geolocation? Where are you located at?
So I'm in Pune, India right now. I'm in Ayuka. It's about 6 in the afternoon.
And it's about 6 in the morning here in Phoenix, Arizona. So we're separated by about 12 and a half hours, somewhere in there. Very cool. And Soumya, is summer approaching in Pune?
Summer is already here. It's very hot.
Here. That's okay. I can say the same thing about Phoenix too. Summer's already here. Very cool. Very good. And what's your position there in Pune?
So I am a senior research fellow. I'm in 5th year of my PhD.
Oh.
Hopefully I'll submit this year and defend. Fingers crossed. Yeah, but I plan to finish up by the end of this year.
Cool. Well, let me be among the first to say, well, congratulations, Dr. Roy. Very good. That is awesome. I'm very happy for you. And Soumya, what do you like to do for research?
So I am a solar physicist. I mainly look at our closest star, the most resolved star you can have.
Absolutely.
I mainly focus on solar flares. So anything related to flares or eruptions happening from chromosphere to corona, I mainly look at the energetics.
Nice.
And I am also part of the recent Indian solar mission that went up, Aditya L1. So I'm part of the near ultraviolet imager team. I mainly work on data reduction pipeline and hopefully some initial science that will come up very soon.
Very nice. Very cool. I predict an awesome PhD thesis. So very good. And that is going to bring us to this very lovely APJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Evolution of the ratio of Mg2 intensities during solar flares. And Soumya, take us away.
Thanks, Frank. So I started this work long ago. I would say around 2021-ish. And this paper is with my PhD author, PhD supervisor, Durgesh Tripathi.
Good
shout out to him. He helped me a lot during the initial phases of my PhD. So there is a bit of a backstory to how this article came about.
Okay.
So when I joined Durgesh initially, we were sort of gearing up for assembling like I mentioned, I was part of the near ultraviolet imaging team suite, which is called Solar Ultraviolet Imaging Telescope on board Aditya L1. So I joined as a team member of that payload, and we were sort of gearing up to getting various parts like filters and shutters and stuff like that, and starting to assemble. Now, I'm not an instrumentation person, so what I had been initially part of the team was as I was looking at doing some initial throughput modeling, like what kind of SNRs you can expect, what is going to be the projected observations and stuff like that. So in context to that, we have two narrowband channels in onboard suite, which are narrowband 3 and 4, which specifically look at the magnesium 2 K and H lines. Okay. Those are 0.1 nanometer FWHM lines. And we were going through whatever previous results or observations exist to sort of see what kind of science we can do. Yeah. So that is where this paper comes from. IRIS is a NASA mission interface region imaging spectrometer, which has been there and provides a great view of the sun for a very long time. But one of the key differences from IRIS to SUIT is it's a spectrometer and also a slit jaw imager, but it only observes certain regions of the sun, whereas SUIT is going to observe full disk continuously. Very cool. But then again, because we needed some context to what kind of sciences we could do, and I am interested in flares, so that is where this paper comes from. I looked at IRIS data to sort of see what kind of things we can do with SUIT.
Nice, nice. That's great. So, how you add the story behind the paper. Very good.
Yes.
Okay.
So Solar flares, we know we have been observing them for a very long time. It's one of the most enigmatic things happening in our solar system. The strongest magnetic event you can see in our solar system.
Mhm.
And we have been observing them in optical, H-alpha, calcium-2, and certainly magnesium-2. So the magnesium-2 HNK lines are a bunch of very special lines. They
Yes.
essentially happen because of transition to same level from two finely split upper levels.
Yes.
And they appear around 2796 angstrom and 2803 angstrom.
Okay.
And people have been observing flares in these lines for a very long time.
Yes.
So from when iris appeared, we have had imaging observations and spectra also. And even before that, people have had full disk integrated spectra when we didn't have observations imaging, spatially resolved spectra.
Yes.
And there have been two main papers which were very interesting to me. So one is cited right here, KR15, who observed a bunch of flares in magnesium-2 lines from iris. And they were using the intensities in the magnesium-2 lines to comment about the local optical depth or opacity of the medium.
Yes.
So if you look at the first equation 1,
Okay.
that essentially tells you about the how the collisional strength between these two levels is related.
Okay.
And as you can see, it depends on a lot of things. It depends on the threshold, so the energy of the ionization energy of hydrogen, which is IH. And then you have your statistical weight of the individual levels, which is your omega I.
Yes.
And your Fij is the collisional strength between those two transitions.
Yes.
Now, in optically thin conditions, these two lines, because they are very finely split, they're very close, the two upper levels from where these transitions happen, the escape probability is almost equal of the photon. So
Yes.
the whole ratio reduces to just the ratio of the two collisional strengths, which in this case is 2:1. So whenever you have the medium optically thin, this ratio would be 2:1. And any other case, when your medium is getting optically thicker, it would start to become lower than that.
Yes.
So whenever you get the intensities of this line, looking at the ratio of these two lines, you can comment about how the local optical depth is evolving.
Oh, cool. Very cool.
So,
I'm with you.
so now what happens in a solar flare is, because you have a lot of plasma flowing down from corona to chromosphere, getting dumped, and then all those plasma heating up the local environment and then again moving up because of the buoyancy along the loops.
Yes.
What we thought was all of this should be manifested into the optical depth, because you're essentially changing the density as various layers.
Yes. Okay.
So, and there had been observations, as I mentioned, from a very previous paper, Lemire et al., 1984, from Orbital Solar Observatory 8. It's a very old paper where they looked at the magnesium lines and the calcium lines. But these are again full disk integrated observations, so they had no spatial resolution, but they did see change depending on the timing of the flare. When the flare was happening, they did see change in the ratios, and they argued that this was probably happening because of localized heating and some opacity effects.
Cool. Okay.
So that was our baseline to look at these two papers. So we picked 3 flares, one M-class flare, one X-class flare, and then C-class flare, because you're looking at 3 different energy scales. And we wanted to see if there were any differences. And the other thing we wanted to look at was there hadn't really been any study where people looked at how these changes also depended on magnetic field strength, if there was any dependence.
Yes.
Because again, solar flares are magnetic events, so supposedly there can be some dependence. So that is why you also look at the photospheric magnetic field. So if you go to figure 1.
Yeah. This is the M3.7 flare. Here we go.
Yes. So this is the M3.7 flare that we looked at. The left-hand curve is the light curve from soft X-ray. So that essentially tells you when the flare peaks.
Yes.
And at 2 different channels of GOES. The middle panel is slightly tricky. So the bottom panel is AIA 1600 angstrom observation, the green background that you see.
Okay.
You can see the flare ribbons there in white, which are marked by 2 arrows. So that is the flare happening in 1600. You can see a big sunspot there at the right-hand side.
Yes.
And then the overlaid white box on top is what IRIS observed. Now, I mentioned to you before that the key difference from IRIS and what our instrument is going to do is IRIS never observes the full sun.
Right.
So only that box region is what IRIS observed. And even within that dot dashed box that you see in the middle, that is the extent of the spectrograph. So that is the region that the spectrograph scanned. Okay. And from there, you have the spectra.
Okay. Gotcha. I'm with you. Mm-hmm.
Yes. And on the right-hand side panel, panel C, you have the photospheric magnetic field measurement, line of sight magnetic field measurement from photosphere from the same region. So that's in Gauss, the red and blue. Yes. And again, the black box is the region that IRIS observed. And the magenta dashed box is the extent of the spectrograph. Cool. So now the key idea is, this is slightly complicated because you're taking 2 different spacecrafts on orbit and trying to align them so that you get the spectra and the magnetic field of the same pixels, and then you can comment. Yes. So IRIS, although we are using magnesium spectra in our analysis, IRIS also provides you spectra from 1400 angstrom, which is the silicon 4 line. Okay. Which is pretty close to 1600 observation that I'm showing here, the AIA observation. So what we do is we use the images from IRIS in 1400 and images from AIA in 1600 to co-align them. Okay. So that your IRIS 1400 observation and AIA 1600 observations are now co-aligned. You have a 1-to-1 pixel correspondence between these 2 observations. Yes. Okay. And then you go back, you take your AIA 1600 observation and you co-align it with the magnetic field measurements from AIA. Okay. So you have a 1-to-1 correlation between your IRIS 1400 observations to AIA 1600 observation and AIA 1600 observation to your magnetic field observations from AIA. Yes. So hence you have correlated your IRIS 1400 observations and magnetic field measurements from AIA. I'm with you. And now you again go back to your IRIS observations in 1400 and you take IRIS 2796 angstrom observations, which is your magnesium observations. Yes. And you co-align them. So you have finally co-aligned your magnesium observations and your magnetic field observations. Gotcha. It's a very involved process. We just glossed over it very quickly, but that's it. That is essentially, I would say, the main crux of the whole work, that you have to do this alignment very carefully. Yes, yes. And so now what you end up with is within that small rectangular box at the middle of the field of view, for each point, you have the spectra and the photospheric magnetic field. Yes. So now we can do some interesting analysis. Yes. So now, if you scroll down. Okay. Okay, just absorbing table 1 there for a sec. Okay. I have a co-aligned raster image of the. Okay, so this is describing again the details of the whole M-class flare that happened. This whole box, each of these panels is actually, again, AIA observations, 304 angstrom, which is very chromospheric. And the white dashed box shows you the raster scan of IRIS again. Yes. So what happens is at initial panel around 1330, the flare arcade erupts. And then you see 2 filaments at panel B, 2 filaments in the top erupting and one moving towards left, the other one moving away towards right. Okay. And the 2 flare ribbons below surge down and sweep across the IRIS, the region that the IRIS raster was scanning. So that is our interesting plasma that we're looking at through our spectrogram. And that is the portion we want to look at. So then again, this shows how the flare evolves, how those ribbons that went through the IRIS observation actually goes on and reconnects to the other side of the event. And then it becomes very bright throughout the IRIS spectrogram region. So the spectra from this flare ribbon is what we are going to use to look at what is happening there locally to the plasma there. So again, as I described earlier, we pick up this iris raster scan and align them to the magnetic field observations from AIA.
Mm-hmm.
So we end up with, if you scroll down again.
Yeah, sorry. Beautiful. Very beautiful picture. Image. And ooh. Figure 3?
Yes, figure 3.
Okay.
No, figure 4, sorry.
Sorry, all good.
So this is what you end up with. The panel A and panel B are essentially your intensities in the two lines, H and K.
Okay.
And your panel C is the magnetic field measurement from the same region, co-aligned, and of course, binned down to same resolution. These instruments don't have same resolution. So that is another thing you have to be very careful about.
Yes.
But essentially what you end up with is you have this, as I was mentioning, you have the spectra from each and individual pixels, so you can get the intensity, and you also have the magnetic field measurements, so you can try to correlate them.
Yes.
So what we would start to do now is we pick up the spectra and start fitting them with Gaussians. We're physicists, and
we
try to simplify our life. Although the magnesium lines can be very tricky because it shows central reversal and various other stuff. It's optically thin line. It's a very complicated line.
Okay.
But to make our life easy, we just fitted it with two Gaussians and a symmetric background about the line core, so that we mitigate the effects of the background if there is any. So I show the fitting in a figure down below this, I think figure 5.
Figure 5, so you take this, boop, 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 boop. Okay, and now we're gonna plot that. Gotcha. Mm-hmm. Nice.
So yeah. So this is essentially the spectra, the whole magnesium window from one pixel that is marked in figure 4 again with a cross.
Yeah, that's the pixels. Yes, 1, 2.
Yes, that's two specific pixels from the north ribbon and the south ribbon.
Yeah, okay, good.
So the top panel and bottom panel is just the spectra from those 2 points at various times.
Gotcha.
So as you can see, during the early phase, you can have features like there is some kind of central reversal going on here. And then when the flare happens, the central reversal goes away and it's a complete full-blown line.
Cool.
These other bumps that you see between these two lines, these small 2 bumps,
yes,
those are actually some other magnesium lines. We call them the magnesium triplets. So they are usually in absorption, but during flare, they go into emission because of very high temperature and densities. It is the general consensus in the community right now is they're probably one of the best bets if you want to predict when a flare is going to happen by looking at how they're going into emission to time it.
Yes.
But we were not concerned with those lines, but we still fitted them because we wanted to get the contribution from them away in our analysis because we just wanted the K and H lines. So this is essentially showing you how the fitting routine I wrote, how that works, how it's performing. And as you can see, the fit is horrible.
Yeah, it's very good.
Because again, this is a very complicated line and you are just oversimplifying by assuming that you can fit it with a Gaussian. That's not how it works. But still, we found an interesting trend that seemed very interesting to us. So which is demonstrated in figure 6.
Figure 6. Okay. So we're going to take those.
Yes.
Boom. Let's go bigger.
So the red line here is just the X-ray, soft X-ray light curve from GOES that I had shown earlier.
Okay.
And the peak of this light curve means your plasma has completely thermalized. So the reconnection has happened somewhere before that, because in flare, soft X-ray usually peaks before hard X-ray. And then you convert all of that non-thermal population of whatever you have, electrons and ions, into the thermal population.
Yes.
So there is a nice correlation between, which is called a Neupert relation. It's usually proportional. But what we did see was, even though the fits were horrible, if you take the total intensity under those fitted Gaussians to calculate the intensity of those lines and then take the ratio, because we knew that these ratios of these intensities tell you about the optical depth of the medium.
Correct.
There seems to be a correlation with the GOES light curve.
Uh-huh.
So the green points here is the point from the south ribbon, and the black points are the points from the north ribbon.
Okay.
So there is a peak earlier than
Yes.
the soft X-ray peak, and then it dips down.
Yes.
And what that means is the plasma environment is getting optically thinner around that time period. And
Yes.
that would also coincide with slightly earlier when you would expect the hard X-ray peak, and that is when your flare sort of starts happening. The reconnection is happening. That's what
Cool.
our standard model tells us. So
Okay.
we thought, maybe something is there, even though the fit is horrible. So how do you proceed from here? One thing you can certainly do is you can stack so that the local irregularities of the spectral shape goes away because you are essentially stacking.
Yes.
So what we did was, because we have the magnetic field co-aligned, we know what the magnetic field values are at the photosphere for those points.
Yes.
We bind various pixels according to their magnetic field strength.
Okay.
So given some magnetic field, we are taking the spectra and stacking them. And what happens in turn is you end up with much well-behaved spectra because you're averaging out local irregularities, let's say, whatever is happening in the plasma. So if you go down to figure 7.
Okay. Cool. Figure 7. Figure 7. Fitted line profiles. Okay, let's zoom in a little bit. Here we go.
Yes. So what this figure is essentially showing you is the spectral profile for various magnetic field strengths from various time. And as you can see again, by the magic of stacking, because we have erased a lot of spatial variations,
Yeah.
they end up to be much more well behaved, and the fit is much more nicer. So we can proceed with these fits much more confidently. And the other thing we also did was initially we were fitting the whole window. And as you saw that those triplet lines did come into emission, there can be other very small lines which can also come into emission within the whole window. We restricted ourselves into a very small wavelength window so that we pick only those lines separately and we fit them separately.
Yes.
And so we fitted them separately. We calculated the intensities as a function of time, and also the bindings we did as a function of magnetic field. And we did see something interesting coming up. This trend that we had seen earlier of the optical depth changing actually does come up very well after you do all this analysis.
Cool.
So in figure 8, we showcase that.
Okay. Figure 8 and K to H line intensity. Cool.
So this is again the line intensity, essentially a proxy for your local plasma's optical depth as a function of the magnetic flux density at various times. So if you look at this, the red dot dashed line, the histograms of red dot dashed lines, they start at 1307. And then they continuously keep rising. If you look at it, the blue, then the green, as time progresses, the line intensity ratio, irrespective of what magnetic field strength you're looking at, they keep increasing. That means your medium is getting optically thinner.
Yes.
Because your flare is happening and you're dumping a lot of energy. And so you're heating up the plasma.
Cool.
And then around 1341, the medium is the optical, if you can call it optically thinnest, the most optical thin the medium gets.
Right.
And then because from your corona, you dump a lot of material, the electrons and the ions into the chromosphere, where you're looking at the magnesium lines. Your magnesium lines generally form in chromosphere, which is lower than the corona. You essentially dump a lot of material very quickly. So the density near the foot points of your flare loops increase very quickly, a lot. So that is why your medium again becomes optically thicker. It should. So that is what we see around 1357, that the ratio drops very quickly.
Yes.
So essentially what you're seeing is an indirect effect of all this plasma flows happening throughout the whole region as a function of time. And the other thing is, I was sort of surprised by this initially, that this does not depend, it doesn't seem to depend a lot on the magnetic field strength. It's happening ubiquitously around the whole region.
Yeah, all across.
Yes. So the next thing to look at was, this looks nice that this is happening as a function of time. So we can look at this as a function of time. So that's what our figure 9 is.
Okay, let's go to figure 9, figure 8, figure 9. Ooh, here we go. Okay.
So this figure essentially shows you how the K2H line intensity ratio from various magnetic field strength binning behaves with respect to your soft X-ray light curve. So the red line is your soft X-ray light curve that
Yeah, we saw
tells
it.
you how the thermal nature of the plasma is evolving. When you thermalize the total plasma, you sort of reach the peak in the red line. So that is your thermal peak, and then your flare loops slowly start to cool. So your output in the soft X-ray is also slowly decreasing.
Right, yeah.
And if you look at the line intensity ratios from various field strengths, you see that they start at a general level of, let's say, somewhere in between 1.17 to 1.2.
Yes.
They slowly start rising.
Yes.
They have a peak around 1340.
Yes.
So that what we are trying to say is that is when your plasma is most optically thin, because your flare happens and it dumps a lot of energy into the plasma. So your plasma your local medium gets optically thin.
Yep.
And then after that, your electrons and ions from the reconnection side comes down across the loops and hits the chromosphere. You dump all those plasma, a lot of material, into chromosphere very quickly. So that is when your plasma thermalizes, because you're dumping a lot of plasma very quickly into the chromosphere. So your plasma thermalizes and the density increases a lot also. So your optical depth decreases.
Okay.
So medium becomes optically thick and your plasma becomes thermal. So that is when you see your peak in the gauge soft X-ray.
Very
So
cool.
everything tallies out very nicely.
Yeah, that's a nice story. Very good. Very good.
So when we saw this, we were very excited. Maybe we can look at how all these flows that is happening in flare. People usually look at them through spectra, through measuring redshifts and blue shifts. Maybe there is an indirect way to measure this through just the intensities, because that's the story it's telling you. And so then, because again, it was driven by our science case we were trying to look at, because we are imager, we don't have a spectra. This is helpful for us. Again, the perspective of SUIT, the mission I'm working on. So let's look at some other flares. That's what we did.
Okay.
So the figure below is an observation for an X-class flare, an even bigger flare.
Yes.
And this is again going very similarly to what I described, how we prepare all the data, we co-align everything.
Yes.
And then we end up with co-aligned rasters, which is probably shown below.
Okay, I'm with you. Yes. Okay.
So again, if you go to figure 11.
Oh, sorry. Figure 11. Okay, here's our intensity maps.
So this is your intensity maps and your co-aligned magnetic field. You can again see where the brightening is happening in magnesium. You see we overplot those contours here in the magnetic field measurements.
Yes.
And that is again happening where you have closer to your zero magnetic field, because you expect the brightenings to happening near neutrality, where your positive and negative field lines would happen. And so then we try to see again what happens to the K2H line intensity ratios very similarly as a function of time. So that is the figure 12.
Yes. Cool.
And we were very disappointed because you don't really see anything happening. Very like there is a peak that happens, but it's not as, how to put it?
Pronounced?
Not as pronounced.
Okay.
Not as well behaved like the M-class flare.
Yeah.
And then we were like, okay, cool. Let's look at another C-class flare. And if you see anything, so that is the next flare that we analyze.
Right here. There's our C-class. Okay.
So again, very similar figures, your 1600 observations that you use to co-align the magnetic field on the right-hand side. And with all those, you end up co-aligned magnetic field and intensity measurements, which is shown in figure 14.
Yes, I'm with you. 14, there's our lineup.
And then on the right-hand side in figure 15, you can see the same figure.
Yes.
The soft X reflux and the K2H line intensity ratios. Here again, you see the change very clearly in the optical depth. All the changes in the values in optical depth are much less pronounced in this case, which is than the M-class flare and also the X-class flare, which is what you would expect, because So all the flare classifications, C, M, and X, are essentially going in terms of how much magnetic energy you release. So a
Yes.
C class flare is a very small flare, so it's a lot less energy involved compared to an M and an X class flare.
Yes.
So all the velocities, bulk velocities of the plasma involved in this would also be much lower.
Yes.
So the change in the optical depth is much less pronounced, but we do see a time
Yeah.
that the temporal behavior, let's say, of the
Mhm.
change in the optical depth is very similarly uh, as we had seen in the M class flare. So again, we were happy. We were seeing something very similar to the M class flare. But the question now became, why don't we see anything in the X class flare?
Right. Right.
Unfortunately, we only speculated in our paper.
It's okay. We'll
So there can be a lot of things that can happen because the X class flare is very big. What can happen is that the downflows are so fast that your raster scan doesn't have enough cadence to catch it at all.
Oh.
So by the time you have come back to the next
Blurred.
scan, everything has already happened.
Yeah, yeah. Yeah.
Or the other thing that could have happened is,
Okay.
again, because magnesium is a very complicated line,
Okay.
and we are just simplifying the opacity relation to approximation, the opacity would actually also depend on how the local plasma is being ionized.
Yes, always.
And our treatment doesn't really take care of that. So what could have happened is some ionization states behaving very differently for the X-class flare. And that is something we actually need to look into, looking at data of other X-class flare to see if that is actually what is going on.
Okay.
So that is where we were at when we submitted our paper.
Cool.
And then we had a very helpful referee.
Yay.
Who really went through our paper very carefully. And
good referee.
He or she, the referee wanted us to
the report,
compare our method to some previously existing method, how they compare with some previously existing methods of looking at the magnesium lines.
Yes.
So as I was mentioning, there was a paper that we were closely following, a paper by Kerr et al., Graham Kerr.
Yep.
What we do is we fit the line intensity profiles, the spectras with Gaussians.
Yes.
What they were doing is fixing a window, let's say some lambda1 to lambda2, and just adding the spectra values within that to calculate the intensity.
That is a little different.
Instead of fitting, and then taking the ratios to see how the opacity behaves. Yes. So our rationale for fitting was magnesium is the whole window is a very tricky window. You don't know how the background behaves. Some other line can go into emission. So we wanted to exclude them.
Yes.
And the referee told us, why don't you look at and compare how all of this behaves? So that's what we did. Cool. So if you go to the final figure in the appendix, this essentially compares our method with Graham's method, what Graham did for the M-class flare. So again, the red line is the GOES light curve in 1 to 8 angstrom, the soft extra light curve. Yes. The magenta points is the points you get from our method, essentially binning and then fitting the spectra. And the black triangles is what you get from Kerr et al.'s method. So instead of fitting, you take the spectra, you fix some wavelength window, and you sum, and then take the ratio. Yes. So what this shows you is the blue crosses is from the total intensity ratio. So what this shows you is the blue crosses, if you look at them, are by and large behaving very similarly to the magenta points. Yeah. So that means our methods sort of agree. Yes. And then the referee also wanted us to compare, again, as I was mentioning, the magnesium lines usually show you a central reversal. But when the flare happens because of very high temperature and other conditions, the central reversal actually disappears and the line becomes a perfect Gaussian. Okay. So what the referee wanted us to do is when the line becomes perfect Gaussian, you can essentially take the peak intensity ratios instead of integrating the whole line. And that also tells you about, this is very similar proxy for optical depth, and compare how your method works in comparison to that. So that is your black triangles. Okay. And that essentially shows you that, again, the black triangles, so you don't see the black triangles throughout this whole time frame because
right. It's only peak. And how?
It's only there when the magnesium line doesn't show you central reversal.
Right.
But when the lines are Gaussian, you
Right.
see that they behave very similarly to the
Yeah.
magenta lines.
Yeah.
And the other interesting thing is
Okay.
that the black triangles are much more well behaved than the two other methods. And that is because when it doesn't show you any central reversal, you are essentially seeing a much more well-behaved local thermal environment through those lines
Okay.
instead of fitting those lines. So
Yes.
that is why the decrease rather in the optical depth is very well behaved when the line is behaving when the line doesn't show you any central reversal.
Yeah. Right.
So that's about it. That's the crux of the paper. What we essentially did is we took magnesium measurements from iris, and we showed that using the magnesium lines, you can indirectly show the effects of the flows in the plasma
Yes.
that you're seeing during solar flares instead of looking at the velocity structures itself. So this is a sort of indirect proxy of what is happening to the plasma locally.
Very cool. Very cool. Very nice. Soumya, I want to thank you so much for walking us through your very lovely PJ article. Thank you. Let's see. And you kind of touched on a little bit as we went through there. So let me push on a little bit and ask, where do you think we go from here given the published article? Is there additional data to process? Is there new data coming in the pipeline? We do have a new mission going that we talked about. Are there ways to improve this current methodology relative to what went before, and so on? So just sort of next steps. Where do you think we go?
So the first step that I need to look at is look at some other X-class flares.
Yeah.
Why we didn't see anything for that
Yes.
one?
Yes.
My hunch still is our spectra didn't have enough cadence, but we really need to look at that.
It was just washed out in time.
Yeah. But we really need to look at that. And the other thing we again, our primary goal sort of was to have some sort of proxy for imaging observations when our data starts coming in to do some science with our data.
When is that data scheduled to start?
So we actually have started observing. So we are in calibration phase now.
Okay,
and
cool.
we are doing all sorts of like flat fields and scatter corrections and stuff like that.
Yep.
But we will go into like the data will start becoming open very soon. Once we are out of our PV phase. But one of the other things that I am looking at is, so we are doing regular coordinated observations with IRIS. We are in contact with IRIS team. So what we would very quickly do is when IRIS observes some region that you get the spectra from them, we take our imaging observations and do just a correlation of how the intensities correlate with iris spectra. So you essentially fit the spectra, you get an intensity, you take our images, you get some counts, and then you correlate them.
Okay.
And so then immediately from our images, how the ratios also correlate. So then we can use the same method to comment on how the plasma is behaving when a flare is happening or something else is happening, some eruption is happening.
Cool.
And the other good thing is because iris only looks at a small region, it usually cannot give you context about any magnetic interaction happening from some other region on the sun.
Right.
Because we are a full disk imager, we can actually resolve that.
Cool.
So the other key thing we can do is, let's say something is happening in this active region at this corner of the sun. Is that interacting with something else up here?
Right.
We can do an indirect proxy measurements of this after we have done the correlation with iris. So that is something I'll probably do, or someone else will probably do very soon.
Very nice. Very nice. Beautiful. 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 Soumya, thank you so much for walking us through your very lovely article, and I wish you the best in your PhD thesis. It'll be great.
Thank you. Thank you, Frank.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.